question number 6 says the reaction of sodium metal and oxygen gas produces sodium oxide. And then it's asking us to determine the number of grams of sodium oxide produced by 100 grams of sodium and 60 grams of oxygen. Next we'll have to determine the excess reactant and how much of it remains, and then finally we're determining the percent yield. So the first thing I'm going to do is write out this reaction. And so the reaction of sodium metal, so Na, reacting with oxygen gas, so oxygen's a diatomic, so I'll put a subscript of 2, produces sodium oxide. And I'll just kind of do my crisscross up here at the top. Sodium is +1 and oxide is -2. So sodium oxide's formula is Na2O. Now I just need to balance this reaction here. Na2O and oxygen. First I'll balance the oxygen out by putting a 2 in front of Na2O. Then I can put a 4 in front of Na to balance out the sodium, and I'll just fill in a 1 here. Now that I have a balanced chemical equation, we can go ahead and calculate the theoretical yield of the reaction by converting 100 grams of sodium to an amount of sodium oxide and 60 grams of oxygen to an amount of sodium oxide. So we'll start with those two given values, 100.0 grams of sodium. And we will first go from grams of sodium to moles of sodium. And then we shall go from moles of sodium to moles of sodium oxide. And of course you could go all the way to grams, but I'm just going to convert both of my givens into moles so I can figure out which one will be the limiting reactant before I worry about converting into the desired unit of grams. So 60.0 grams of O2. Then we have grams of O2 to moles of O2. And moles of O2 to moles of sodium oxide. Okay, we'll put in some numbers here. Our mole-to-mole ratios will of course come from our balanced chemical equation. So on top of both these conversion factors I can put 2. For moles of sodium, there are 4 moles of sodium in our balanced chemical equation. And for oxygen, there's 1 mole in our balanced chemical equation. Then for my gram to mole conversion, I know that 1 mole of sodium, I can find that mass on the periodic table. That's about 23 grams per mole. And then 1 mole of O2, I'll find oxygen's mass, which is 16, and multiply by 2 to get 32 grams per mole there. And so now all that we need to do is calculate. So I will, in my calculator, type 100 divided by 23 times 2 divided by 4, or you could just do divided by 2. And either way, that gets us to 2.1739 moles of, and I'll actually write that over to the side, moles of Na2O. And then for our oxygen, 60 divided by 32 times 2 gets me to exactly 3.75 moles of Na2O. And so from here we can identify our limiting reactant. It's the amount of reactant that produces less product. So our lower number of product is right here. We will not be able to produce 3.75 moles. We're going to have to stop when we reach 2.1739 moles. So I'll go ahead and cross this amount of product off because we will not be able to make that much. And so we'll identify sodium as our limiting reactant here, and then oxygen is going to be our reactant available in excess. Okay, so now it is asking for our the number of grams of sodium oxide produced, not the number of moles, so we cannot leave this value at moles. We're going to have to do another step to convert our moles of sodium oxide to grams. Alright, so our mole to gram, 1 mole of sodium oxide, we can add up the molar mass. So 23 times 2 plus 16 gives us a molar mass of about 62 grams per mole. And so if we multiply that out, I got 134.8. Let me just check that one more time. So I'll take my 2.1739. Remember, you don't want to round too far there because that's an intermediate value. So when I do this, I get 134.7826, but I do need to round that to my correct number of sig figs. And our given value here has 4 significant figures. Make sure you use the given value from the problem to do sig figs, because notice up here that 100.0 has 4 and 60.0 has 3, but if we were just to write 100 without the 0.0 part, that would look like we should round to just one significant figure, and we should in fact keep 4 here. So 1, 2, 3, 4, we'll look at that 8 to determine whether to round up or stay down. And of course here we are going to round to 134.8, and our units should be grams of Na2O. So there's our first answer, and it gives us a blank to put it on, so we should definitely write that into the blank up here, 134.8 grams of Na2O. Make sure you fill in blanks when they are given. So there's our first answer. Then it asks us how much excess reactant remains. So we know that some of the oxygen will get used up reacting with this 100 grams of sodium and producing the 2.1739 moles of sodium oxide, but not all of the oxygen is going to get used. So we need to figure out, if we produce this many moles of sodium oxide, how much oxygen did get used up in that process. And so I'm going to start with my 2.139 moles of Na2O of sodium oxide. You could also start with anything that's stoichiometrically equivalent to that amount. We could start with 134.8 grams of sodium oxide. We could start with 100 grams of sodium, anything that is stoichiometrically equivalent. And then we'll go moles of Na2O, 2 moles of oxygen, O2, and then we will go from moles of O2 to grams of O2. Figure out how much is used up. So in our reaction we have 1 mole of O2 in our balanced equation and 2 moles of Na2O. And then we know that 1 mole of O2 is equal to 32 grams. We already used that molar mass once. And so we just calculate this out here. So let's see. When we calculate this out, let's do this in a calculator. 2.139 divided by 2 times 32 gets me 34.224. Close to that. We actually might want to hold on to more significant figures here in our answer. Just go back and use that full value. Oh, and I actually typed it in wrong here. 2.1739. That's why I'm off a little bit from what I expected. Let me fix that here. 2.1739. Take that full value here. I just recorded it wrong, so it's so easy just to make a small mistake in these problems. So let me calculate again. 2.1739 divided by 2 times 32. So this time I got 34.7824, which is the answer I was expecting. 34.7824. We just need to round to correct sig figs, and we should round to 4 in this answer as well, because that was our original value. So let's round this to 4 significant figures. 34.78. And this is the number of grams of oxygen that were used. So now we need to figure out the excess, and we'll do that through just some simple subtraction. We started out with 60 grams of oxygen, 60.0 grams, and we'll subtract out the 34.78 grams that were used up. to get our amount of excess. Let's see, 60 minus 34.78 gives me 25.22, but since we are subtracting here, our sig figs have to do with decimal places. So I have 1 decimal place here and 2 here, so we need to round our answer just to 1 decimal place. So I'll round to 25.2 grams of excess O2, which is our second answer, so we'll fill this into the blank at the top. 25.2 grams of excess O2. And then last but not least, it asks us to calculate the percent yield of the reaction if we get 98 grams of product. And so we know that percent yield is equal to the actual yield, which always has to be given, divided by the theoretical yield, which we calculated. So the actual yield, it tells us, is 98 grams. And then our theoretical yield we calculated in part 1 to be 134.8 grams of sodium oxide. So we'll just divide by that, 134.8 grams. And then of course we'll multiply by 100 to get to a percentage. So 98 divided by 134.8 gives me about 72.700%. And of course we should round this to correct sig figs. Our value on top has 2 sig figs and the bottom has 4, so I'm going to round my answer to 2 sig figs as well. So this is going to be approximately 73%. And we will fill in that last blank, 73% yield. And we've answered all the components of this question. We're done.